Hello. Today we are going to discuss regarding the decision making device. Okay. So after last day, what we have discussed, we have developed the whole derivation of bit error rate or probability of error for BPSK, and after the derivation we got this expression, which is nothing but the average probability of error for BPSK. Now, at the receiver side of BPSK, we have shown that Y, which is nothing but the observation, which is coming into a device which is decision-making device, in which there is some value which is known as threshold. Above the threshold value, receiver will give the result in favor of 1, and below the threshold value, receiver will give result in the favor of 0. That is mentioned here. That if observation is greater than 1, sorry, if observation is greater than 0, then 1 will be at the output. If observation is less than 0, then 0 will be at the output. That means this 0 in the square box I have shown, this 0 is the threshold value, threshold 0. That means this one. Okay, so how this 0 is coming? Now we are going to derive some expression. We are going to uh, perform some derivation, and we can prove that this we are going to prove this expression. We are going to prove this expression. Okay. So before that, that is one case that we are going to do. That means this expression we are going to prove. Uh, Find out in the next topic actually. Find out threshold for BPSK. That means we are trying to get this expression. Okay, where 0 is a threshold. Before that, we will discuss that, suppose for an example we have taken that if the transmit bit is 1 and detected bit is 0, then what is the probability of error? Definitely the probability of error will be half of ERFC in the bracket root of EB by F naught. How? Okay, so transmit bit is 1, detected bit is 0. That is what we have to calculate. We have to calculate P E in the bracket 1 probability of error for the actual bit 1 which is transmitted. Okay, to do that, we have to start in this way. Observation for BPSK, that is Y, is your plus root of EB minus root of EB. Noise term is there for 1 or 0. Mean of the observation is this 2. Already we have discussed for 1 and for 0. Mean of noise is 0. Variance is n naught by 2 for 1, for 0 both. Probability density function. Okay, so actual bit is 1. Detected bit is 0. actual bit is 1. That is why we have to take probability density function for 1, which is this one. Already derived this portion. Okay. Now, for this, this is the curve which extends from minus infinity to plus infinity, having some threshold value. Okay. So actual bit is 1, which is transmitted, but detected bit is 0. That means detector. That means we have to perform the integration process probability density function in this region. That is minus infinity to 0. Okay. So at receiver, 0 is detected. Actual probability of error, actual bit transmitted is 1. Minus infinity to this 0 from this curve, minus infinity to 0, this region only this region, remember. Okay. Minus infinity to 0, this one. Okay. So total probability is 1. 1 minus 0 to infinity means only this region only. That I have written here. Okay. Now, very simple thing, as already we have done, just you put this one instead of this. You put this expression here. Then what we are going to do? Take this portion out, e to the power minus z and not, by considering this integration process. Now we have this one. This thing will be giving us this expression. Actually, we have done this same thing. Okay. Now minus some property of ERFC where we are going to use, and finally we will get this one, which is nothing but probability of error for 0 also. So average probability of error is this one. Now, so whatever, suppose bit 0 is transmitted, 1 is received, same derivation. 1 is transmitted, 0 is received, almost the same derivation. Okay, and already we have done in the last class the same thing. Okay, today some recap. We did some recap because these things you need to have some practice. Without practicing, you cannot get the best result from this, because this is total derivation is there. Okay, understanding derivation. Not only the derivation, you have to understand the basic things, basic theory you should know. Then you can understand these simple derivations. Some integration. We are doing just nothing but some integration, changing some limits, and using the concept of probability. That's all. Okay. Next very interesting thing is that again and again I am telling that threshold is 0. If observation is greater than 0, 1 is detected. If observation is less than 0, then bit 0 is detected. So 0 is the threshold value with which the observation is compared. So how this 0 is coming? To find out the threshold for BPSK, we did everything in terms of or with the help of BPSK modulation. You can do it by taking another example, another modulation technique, no problem. So what we are writing, see, one important term now we are going to introduce, that is maximum likelihood detection. This is a kind of detection, one type of detection, maximum ML is nothing but maximum likelihood detection. There is some detection rule. Okay, what is that? So first you should know that probability of occurrence of 0 denoted by this, probability of occurrence of 1 denoted by this, both are equal, and if both are equal, so total probability we know that is 1. So both the things are equal, so individually both are half, because total probability of anything is 1. So probability of occurrence of 0 is equals to probability of occurrence of 1 is equals to half. So we can write down this one. This is known as maximal or maximum likelihood detection or maximum likelihood concept. Okay. When the probability of occurrence of 0 is equals to probability of occurrence of 1. Both are equal. Okay. So what is the maximum likelihood detection rule? Probability density function. This is also probability density function or likelihood function. Both are likelihood function. That is why whenever we are performing the integration over this or over this, we are getting same result. Half of ERFC root of EB by L naught. Why we are getting the same result? Because this and this both are maximal likelihood function. Definitely both are probability distribution function or probability density function, but both are maximal likelihood also. So what is the detection rule? Detection rule tells you that if probability density function of 1 is greater than the probability density function of 0, then bit 1 is detected. If it is less, then bit 0 is detected. That is only the detection rule. Very simple. Just perform the calculation of the probability density function. If it is greater, that means 1. If it is less, that means 0. Simple thing. So this is the detection rule or maximum likelihood detection rule. This one. This one. So we know just now we have derived, many times we have derived the probability density function for this and for this. Just to put these two values in this equation, Okay. In the next page, we are going to do that. Just here I just substitute this value of for 1 or 0. Derivation is in the last classes we have discussed how these things are coming. Okay. All the class sequentially try to follow, otherwise nothing, you cannot understand anything actually. Okay. Now simple mathematical things that we are going to do. Okay, cancel out these two things. This divided by this that I am writing here. E to the power minus 1 by n naught I have written, taking common this minus this whole thing. So we have something like this, e to the power, cancelling out your this term, and this term and this term. Okay. So finally we have 4y root of EB by n naught. This one, e to the power. One is there. One is coming from here. Okay. Then, but you take both side natural logarithm. Both side you take natural logarithm. That's all. If I'm taking natural logarithm both side, this term will be 0. Natural log of 1 is 0. Natural log of this term will give you only this one, exponential part of it. So from here, this is constant, this is constant, this is also almost constant. So y will be equals to this one. That is why 0 is the threshold value for BPSK, with which observation is compared. Okay, so in fourth module, again, in fourth module, we have used this one. Now in second module, we come to know how these things are coming, how these expressions are coming from where. So these are the link between second and fourth module. Okay, but even though in digital communication, if you are going to do many things, okay, at that time these derivations are very much important. Okay, at that time if you are not very much aware about the 64 QAM, okay, it's okay, but this how these things are occurring, how the derivations are, you have to perform that thing are very important. But okay, definitely in the BTech courses, remember that in the BTech courses, module 3 and module 4 are most important for the BTech. For MTech, module first and second are very important for master degree courses. definitely in EC, in communication portion. So this is our, in whole, we have discussed these things. In short, if I want to say, we have derived from page number 6 to page number 10, what we have derived? We have derived probability of error expression from Gaussian random variable concept, threshold value 0, that also we have seen how it is coming. We have seen that if bit 1 is transmitted, 0 is detected, how much probability of error is there and how to calculate that. These are the things we have just now studied. And before that, we have studied that Gram-Smith orthogonalization process. And before that, we have studied geometrical representation of signals. And before that, we have studied orthogonality property and orthonormality property. So these are the almost all whole thing of module 2 and basic things of module 2. And one more thing I should mention, that maximum likelihood function and maximum likelihood property or detection rule, that also we came to know in this module. So almost all we have covered lots of things in digital communication. So one more thing is left till now. So today we will discuss our okay, today let it be today only we'll discuss. That is actually very important, but not for very important for the case of wireless communication, not for the digital communication, but even though it is in your syllabus, sure, I should mention it. The name is Gaussian MSK. Gaussian MSK is actually minimum shift keying, Gaussian minimum shift keying. Gaussian means what? Gaussian means we have a filter which is having impulse response in Gaussian nature. In Gaussian nature. Gaussian nature is what? Just now we have seen. What is the Gaussian nature actually? Gaussian nature is this one. This one. Minus infinity to plus infinity. That is the Gaussian nature. Some curve which is having Gaussian kind of. Okay. So whatever. In this case, in this case, we have to use some filter which is having impulse response. That impulse response is having Gaussian nature. That is why the name Gaussian is coming. Okay. So very simple thing, and we'll discuss it in a very short way. Okay. First, you remember that it is used. GMSK is used in the case of GSM mobile phone. In that case, mainly GMSK is used. So here we will discuss very interesting. Just to follow some lines. The first diagram. In the first diagram, we have shown you that this is the power spectral level, power level actually. This is the bandwidth. From this x-axis we can calculate the bandwidth. From this we can calculate the power. Okay. Some plot is there of MSK, green color line, MSK. This is the green color line. This green color line and this green color line, a gap in between these two is minus 20 dB. So this is the first lobe. This is the second lobe, then third lobe. So all these are secondary lobes. But this is the primary lobe. So there is a gap between primary and secondary, first secondary lobe. From here we can say that most of the power is contained in the first lobe. That means most of the information is contained in the first lobe. For the case of GMSK, for the case of MSK. But you see, for QPSK, blue line, you see, this is the primary lobe, this is the secondary lobe. So the gap is only minus 10 dB. That means if I am comparing in between QPSK and MSK, in the case of MSK, most of the power is contained in the first lobe as compared to the QPSK. That means most of the information is contained in the first lobe. So you can say that MSK is a much more power efficient as compared to QPSK, but MSK is not much bandwidth efficient as compared to QPSK. Why? Because you see the MSK green line, this is the bandwidth up to this. This is the bandwidth of MSK. Now you see QPSK blue line. This is the required bandwidth of QPSK. So definitely the required bandwidth for QPSK is less. We will calculate the bandwidth for the first lobe from 0. Okay, we are calculating the bandwidth first null. This is the first null to 0. This is the first null to 0 line, y-axis. This one. So for QPSK, we have seen that the required bandwidth, this width actually, this width is less than this width for MSK. So we can say that required bandwidth of QPSK is less as compared to MSK. That means QPSK is a more bandwidth efficient but less power efficient. That is very important conclusion from this first diagram. So we can compare QPSK and MSK in this way. Interesting. Now the next diagram, the second diagram, see the dotted line. This is the diagram, dotted line, power spectral density for MSK. This dotted line, where you can see 0 and minus 20 dB. That is the second lobe. That means it's a gap is there, as I have shown here, green color line, 0, and here it is minus 20, and this is 0 for MSK. That means in the first lobe, most of the power is contained, most of the information is there, but bandwidth is more. For MSK, this is the first lobe, maximum power is there only in the first lobe. Okay, but bandwidth is, this line is the bandwidth. This red color line is the bandwidth, required bandwidth for MSK. Now we are going to introduce another thing which is known as GMSK, where the required bandwidth will be less without affecting the power efficiency. That means if let me tell, this green color, this line is the bandwidth of GMSK, required bandwidth of GMSK. Follow the blue color line. Sorry, follow this blue color line. This is what required bandwidth for GMSK, and it is less than the required bandwidth of MSK, because required bandwidth of MSK is denoted by this red color line, required bandwidth of MSK, which is more than the required bandwidth of GMSK. So this blue color line denotes the required bandwidth of GMSK, and this red color line denotes the required bandwidth of MSK. But for both the cases, you can see that first lobe and the next lobe is having a good gap in between. For MSK, first lobe and second lobe or secondary lobe is having minus 20 dB gap. In the case of GMSK, it is far better. First lobe and second lobe, there is almost all minus 30 dB gap. So GMSK is far better than MSK in both point of view: power contained in the first lobe or main lobe and required bandwidth. So GMSK is much better in terms of power, in terms of bandwidth than MSK. And definitely there is good comparison between MSK and QPSK. Okay. So directly I'm not coming to the GMSK. Important thing is that I am covering from QPSK, then MSK, then GMSK, so that you can understand then why we are interested in suddenly in GMSK. because GMSK is providing you both the things, power efficiency, bandwidth efficiency. In the case of GMSK, in the first row or in the main row, most of the power is contained and required bandwidth is less as compared to MSK. So it is much better than MSK in both the terms, power and bandwidth. That is the things we have mentioned here. That is the I have written here that from the power spectral density point of view, MSK and QPSK, we can infer almost 20 dB decay of the side lobe from the primary lobe in the case of MSK. There is a 20 dB gap between primary and side lobe in the case of MSK. Most of the power, next point, most of the power is contained in the main lobe of MSK as compared to QPSK. Definitely. Most of the power is contained in the main lobe of MSK as compared to QPSK. Because main lobe and secondary lobe gap is more in the case of MSK. Third point, for MSK, main lobe is much wider than QPSK. In MSK, more bandwidth is required than QPSK. So MSK is less spectral efficient or bandwidth efficient. In GMSK, now GMSK introduced. In GMSK, required bandwidth is reduced as compared to MSK by introducing Gaussian filter. Gaussian filter. This is the Gaussian filter. In GMSK, side lobe is 30 dB below the main lobe. GMSK is used for GSM. Okay, 30 dB below the in GMSK side lobe is 30 dB below. You see, this is the GMSK. This is side lobe, almost of 30 dB below the main lobe. Okay, and what is the purpose of this filter, Gaussian filter? Purpose of the filter is nothing but to vary the shape of the pulse, like raised cosine pulse. We have seen that one parameter alpha was there, roll-off factor. Here also one parameter is there, that is your bandwidth and bit duration product. See here, bandwidth and bit duration product is an important parameter for GMS. Depending on that, Gaussian filter response shape is changing. Gaussian filter response shape is changing depending on the value of BT. It may be 0.2, 0.3 and 0.25. Depending on that value, we are getting this kind of different power spectral density lines. So this is the brief discussion of GMSK, and mainly GMSK is used in the case of GSM technology. Okay, so how GMSK is suddenly coming? From QPSK, you have to better to say from QPSK, then MSK, then GMSK. In GMSK, we have introduced one thing, that is the Gaussian filter. Okay, and it is much better than MSK in terms of power, in terms of bandwidth also. This much things just you have to tell. So in short note, this is coming mainly. If you are able to draw these two diagrams now, you will get full marks, full to full marks. If it is 10 to 10, 5 to 5 out of. Okay, so today up to this we have discussed. Here, if anybody is having any doubt, I have given my contact number and WhatsApp number. You can contact anytime for the discussion or for any doubt clearance. Now I am leaving the class.